Welcome to this next lecture of Knowledge and Data. This one is about formal systems. We have just been talking about propositional logic, and propositional logic as one of the most well-known and best understood formal systems is hopefully a good introduction to what we understand a formal system to be. Reminder, what we're looking for is something that allows us to interpret our knowledge and our data that we have somewhere stored on a computer to be interpreted in a predictable way, so that we can derive things wherever we are in the same way. If we have the same basic information, then we can understand information in the same way. So this is the goal of a formal system, that you specify unambiguously some facts of the world, and you have rules and common understanding of what these sentences mean, so that you can interpret them and can derive facts, and whoever has the same information, they will derive the same facts. And this was in propositional logic. If you have a formula in propositional logic, then we all know whether it's valid, whether it's satisfiable, and we all know whether a formula is entailed by some other knowledge base. And this notion of entailment is really the critical notion that we are going to look into in the next slides in a more generic way, and looking at other systems. So to me, a formal system is a logic. So basically you start out from some representation of the world, and you use a logical formalism to deduce new facts that have been implicit in the data but not explicitly stated. So what's the logic? It's a formal language which gives a syntax with all the expressions that are legal, so well formed. What are the sentences that I can write down so that they can really be understood also by a computer as an instance of my language. The semantics tell us what this legal expression mean, and the meaning of each of the sentences with respect to specific interpretations. And the calculus in the end allows us to determine the meaning automatically using some computer programs, some algorithms. We won't talk about calculus here in this course, but we will talk about syntax and semantics, and I want to give some examples. So the first example is a logic of arithmetic. And basically, what kind of statements do I want to formalize? I want to have relatively simple statements, namely that I have a term on the left-hand side and a term on the right-hand side, and a comparator in the middle, so equality, inequality, bigger than, smaller, equal, or bigger than equal. These are the 5 options. And the terms might be either natural numbers with or variables combined with the usual arithmetic operators, plus, minus, multiplication and division. So let's do it more systematically. We have 2 terms with a comparator between them. This doesn't work, so let me go back, sorry. A term is either a natural number, a variable, or a complex term. And a complex term is an operator applied to 2 terms. We are usually used to infix notation, which means that we have the operator in the middle and the 2 terms that the operators apply to the left and the right, with parentheses around. So the first example, x plus 2 is bigger or equal to y, is a well-formed sentence if we don't need the parentheses. So if we are a bit lenient about the parentheses, if you would be really formally correct, then you would need parentheses around the x plus 2. The same holds for the next example. It's x plus 2 plus 4 is smaller than 12 is a correctly well-formed sentence if you suppose that there is a parenthesis around. Whereas the next ones are not, because in the first one, x squared plus y, we do not have a comparator. On the second one, we don't have a comparator to the right-hand side. And in the next one, we have on the left-hand side of the comparator of the equation, we don't have a well-defined, well-formed term because a second number or variable is missing. As I said, we have the problem with the parentheses. We also have that in propositional logic, but here it's well understood, I think, that if you have a sentence that is 7 plus 3 plus 5 is 2x minus 3, it's not really well formed according to the definition I gave above, unless it is clear what is meant, namely that you have, for example, left binding of plus is stronger than the right binding, so you have 7 plus 3 in parentheses plus 5 equals to 2 times x, which also binds stronger than the negation minus the 3. And then we have a clear and unambiguous formula. We know exactly what it's supposed to mean, and we can derive that there is no two different readings of the structure of this language. So this is the intended language, and how do we do this? How we do we define the meaning, the semantics to this is basically truth is defined in terms of assignment for variables. And how does it work? We have a set of variables, and to each of those variables we assign a value in the natural numbers. So then, for example, if you have an inequation x plus 2 is bigger than y, bigger or equal than y, this one is true only if we interpret x in a particular way and y in a particular way. So if we interpret it, for example, that x must be a 7 and y a 1, then we know that 7 plus 2 is bigger or equal than 1, which implies that 9 is bigger than 1, which is true. So this assignment of values 7 to x and 1 to y makes this statement true. So for specific values, this formula can be true or it can be false. So we say that if we have a formula like x plus 2 is bigger or equal to y, then an assignment of values to variables is a model of a formula if the formula is interpreted in its entirety as true. So look at the formula below. If you have x plus 2 is smaller than x plus 3, then whatever you choose as an assignment for x, this formula is always true. So if you choose x is y, then we have 3 is smaller than 4, which is true. If you choose x to be 0, then you have 2 is smaller than 3, which is true. So whatever assignment for x you choose, this formula is always true. The second one is x plus 2 is bigger or equal than y. It's false with respect to a specific assignment. So if we choose, for example, x to be 0 and y to be 6, then x plus 2 is 2, and that is not bigger than 6. 2 is not bigger than 6. So a formula can be true with respect to a certain assignment, and then this assignment is called a model, or in this case, it can be false, and then it would be a counterexample. So that is not always true. And a formula can be always false. So 3 is bigger than 5 is simply not true. You cannot find any assignment to make this formula true. Okay, so this notion of an assignment of values, variables to a domain, in this case the natural numbers, is one of the core notions of a logical or formal system. And based on this one, we can now define the predictable inference in this case. We can say what is entailed by some knowledge we have. So think of the example that we know that x plus y is smaller than 6. The question is, can we conclude that x is smaller than 10? And the answer is yes, of course, if you think about it. And why is that the case? First of all, what does it mean actually given our definition? It means that x plus y is smaller than 6 entails that x is smaller than 10. And this is whatever assignment we choose for x and y that makes the left-hand side of this entailment notion true, also makes the right-hand side true. So if we choose x and y so that the sum of the two is smaller than 6, and x and y are both interpreted as natural numbers, so bigger than 0, then x must be smaller than 10. Otherwise, we would not have been able to find x plus y is smaller than 6. So the definition here for entailment with our arithmetic language is that a formula f entails another formula g if for all variable assignments that make f true, g is also true. And then we write this strange way f entails g here. In other words, f entails g is true in all the models of f. So look at the example on the bottom. If I interpret x plus y smaller than 6 in a way that it's true, then the interpretation of x and the interpretation of y, the sum of these two must be smaller than x. But then I also know that the interpretation of x must be smaller than 6 minus the interpretation of y, which implies that x must be smaller than than 6, as y can only be bigger than 0, as it's a natural number. But then we know that x is smaller than 6, which also implies that x is smaller than 10, so the interpretation of x is smaller than 10. So basically we've proven in this case that x plus y is smaller than 6 entails x is smaller than 10. Because whenever I have a model for the former formula x plus y is smaller than 6, then this is also a model for x is smaller than 10. It doesn't hold the other way around. I can find a model for something where x is smaller than 10. For example, x is 9. But then the left-hand side is not true because 9 plus whatever I choose is not smaller than 6. Let's look at a different example, the logic of concept hierarchies, as I called it. It's not a proper recognized logic, but it's a very nice small formal system that is closely related to what we see later with the languages for knowledge graphs on the web. A concept is defined as an abstraction or generalization from experience or the result of a transformation of existing ideas. That sounds difficult, but think of things like cars, lions. That would be collections of concrete objects, but this can also be objects that are a bit more abstract, such as political concepts and so forth. Doesn't really matter. Here I give you a language which is really about classes of objects. And the only thing you want to say is that one class of these concepts is more specific than the other. So C is a subclass of D, in this case C1 or a subclass of C2, for example, would say that everything that is a C1 is also a C2. So you give some notion of more specific than. The syntax of this language is that we have a finite set of names, and that can be lions, mammals, but also feminism or library concepts and so forth. And they are ordered by a subclass relation. So if we have two sentences, two names in our concept name set, then we can combine them into an axiom of my language by stating that C1 is a subclass of C2. This is the only statements that we can make in our language. And our knowledge base is then just a set of those axioms. So here's an example. Lions are subclasses of mammals and capitals are subclasses of cities. And this together would create a knowledge base. Not very rich, but interesting, or maybe a little bit. Where it becomes interesting is that we can have very simple inference. If you look at the example that lions are subclasses of mammals and mammals are subclasses of animals, then you would like, in some of these cases, to derive that lions are also subclasses of animals. So basically everything that's a lion is an animal. If that is the case, and we also know that everything that's a mammal is an animal, then we want to derive that every lion is an animal. This is not always the case, but it is the case when we talk about classes of objects and subclass relations. And this is what we're going to do here in the semantics, where we interpret the subclass of relation as a subset relation between the instances of the classes. How do we do this? We define U to be a universe, which is just a set of arbitrary objects. Doesn't matter what we choose, but we need to interpret our elements of the language, our concepts, as subsets of this domain. So we have an interpretation function, an assignment function that assigns sets of the domain to each concept. So P of U is the power set, I should say, of the universe, which means the set of all the subsets. And then an axiom, which states that C1 is a subclass of C2, is defined to be true with respect to an assignment to values C1, to classes C1 and classes C2, if the interpretation of the first one is a subset of the second one. So in my statements, I interpret the left-hand side as a set, the right-hand side as a set, and the statement itself is true if the interpretation of the left-hand side is a subset of the interpretation of the right-hand side. And if that is the case, then my interpretation is called a model for the axiom, just as we saw before for propositional logic and arithmetic. An assignment of those values, of those subsets to concept names is then called a model of a knowledge base if it is a model of all its axioms, and an axiom, C1 is a subclass of C2, is entailed by a knowledge base if it's true for all the models of the knowledge base. Exactly the same mechanisms that we applied for propositional logic and that we applied for arithmetics is also now applied in our little logic of concept hierarchies. You probably need an example, and here is an example. So suppose we have a knowledge base with 3 axioms: lion subclass of mammals, mammal subclass of animals, and we want to prove that in those assignments for these first 2 axioms that we can entail that lions are subclasses of animals. So what would be an interpretation? I said that you need a universe, some objects, and I just take the numbers 1, 2, 3, and 4. And I assign the value of the class lions to be the objects 1 and 2 out of my universe. For the mammals, I take the objects 1, 2, and 3, and for the animals, I take 1, 2, 3, and 4. This is one possible interpretation, and I take another one, which now is just the objects A, B, C, and D, where I say lions are the A and B's, mammals are the A and C's, and animals are the A, B's, and C's. And as you see already for the second one, that the second interpretation with U2, I2, I should write down, not U2 here, is not a model. And why is this not the case? Because the interpretation of the lions, A and B, is not a subclass of the interpretation of the mammals. So here already, this axiom, lion subclass of mammals, is not true with respect to this interpretation. So U2 is not a model. I1 is a model. So the first interpretation with the first universe and the lines to be 1, 2, and mammals be 1, 2, and 3, because the set 1 and 2 is a subset of the set mammals 1, 2, and 3. And the second axiom is also true because the interpretation of the mammals 1, 2, and 3 is a subset of the interpretation of the animals 1, 2, 3, and 4. So the first interpretation 1, 2, 3, and 4 with the interpretations is a model. And what you see here is that 1 and 2, the interpretation of lines, is also a subset of 1, 2, 3, and 4 of the interpretation of animals. And this is necessarily so in all the models of knowledge base that has the first 2 axioms true. Why is this the case? Because the subset relation on which the axioms are into which the axioms are interpreted is transitive. So whenever I know that the interpretation of lions is a subset of the interpretation of mammals, and the interpretation of mammals is a subset of the interpretation of animals, then I can automatically know, because of the transitivity of subset, that the interpretation of lions is also a subset of the interpretation of animals, which is exactly the definition for the third one. So basically, this shows that I can have an entailment definition, namely that it follows by my definition of the semantics that lions are subclasses of animals. So what's next? We've now looked at 3 formal systems. We hopefully have convinced you that knowledge graphs are interesting formalisms to study and to pursue. So the remaining thing is to give you a formal system for simple knowledge graphs in a similar style to the propositional logic or the logics that I've just shown, the arithmetic and the concept logic. And this should leave you sufficiently well equipped to start manipulating these logics knowledge bases. And this is going to be what you will have to do in the first assignments. In the next module, we look at the impact of using the web as an infrastructure. And this basically introduces the web of data to you. And the web of data, or semantic web, is a family of formal systems for publishing and accessing knowledge graphs on the web. The RDF language to describe knowledge graphs on the web is the first thing we do next week. And we look at the syntax and the semantics of the language, and basically also look at how you then really can use this language in practice to access and store and model RDF data. And the language is to model richer knowledge, more like the concept knowledge and the concept language, the concept logic that I introduced. They will come in the later modules. That was it for now.